All right, so another week, another practicum. This week's topic is interpolation, and we're going to get to that in just a second. But first, I just want to tell you about what I've got set up here, and we're going to do just a couple of basic methods for cleaning up our data because we've done a bunch of stuff now in our map sets, and we maybe clog them up with a bunch of useless maps as we've been experimenting. So basically what you're looking at right now is the Wadi Hassa 30-meter SRTM DEM from Permanent and the Wadi Hassa survey sites just laid over them here. In our last practicum, we were experimenting with a variety of analyses, including we've done least cost paths, and we did the map calculator, and we made a bunch of maps, some of which maybe we don't want to keep around anymore. So for example, if we go into our map selecting window over here, I've got this slope times 2 that I made last time, which it is what it is, but it was just a demonstration to show you what you could do in the map calculator. It doesn't even mean anything. So I don't necessarily want to keep this map around. I don't want it to be cluttering up my map set. And I want to permanently delete it. And I want to make sure you note that just by doing this and remove, all we're doing is actually removing the layer from the layer tree, but the map still exists in the GRASS database, right? It's still in the location map set. There's physical data on your computer, and so if we go back to select it, it's still there, right? Slope times 2. I could do that. So what if we wanted to really get rid of it for good? Well, there's a whole set of sort of file manipulation tools that are under the File menu. And the ones that we're particularly interested in over here is under Manage Maps. And you see gcopy, glist, grename, gremove. So these are a lot of little fun utilities. If you mistakenly named your map something and you just want to rename it, you can use grename over here. And the way you do it is you select the map that you want to rename. Let's just pick the same slope x2. In the same field here, you put a comma after that map and you just say fun slope experiment, right? And you hit run, and basically the map is renamed. So if I go to load it again in the tab over here, it's actually called fun slope experiment, right? Same exact map, so nothing changed over here, but I just changed the name of it in GRASS. And that's for rasters. The vector tab is here, and there's a whole bunch of other things you can rename. You can also copy maps from one map set to the other. With gcopy, it works exactly the same way. You open it up here, you find the map that you want to copy from some other map set, perhaps from Project 2, the hillshade, and you say, just give it another name, could be the same name. And what it'll do is it'll copy it from the other map set into this one, so that now when we go to look for maps, you see we actually have my hillshade copied over physically, a brand new copy, a different copy from the other copy that's down here, still in the Project 2 map set, but I have a local copy now that I can work on in my current map set. And of course, after we've cluttered up with a bunch of maps, we may want to delete some of them. So this is gremove, and it works kind of differently. Firstly, you have to tell it the type of data that you want to remove, raster. And then you can select from here the maps that you actually want to remove. So you can select multiple maps. I'm going to delete my hillshade, fun slope experiment, right? And the average slope aspect, that kind of stuff. So I've got this sort of list, and you can see it automatically puts the commas here. You can enter it in manually here. If I hit run right now, what it will do is to just list the maps and say, we would have deleted them if you had checked the -F flag. This is a sort of safety measure. It's like the safety on a firearm, just like shows you what would have happened but doesn't actually do it. So you can just do this and double check and say, yeah, these are all the maps I want to delete. I didn't accidentally select one I didn't want. You go back to here and you have to check this flag up here that says force removal. And then when you hit run, those maps are actually gone. So if I go back over here and we look for them, they're actually all gone here, right? Completely and totally deleted from my hard drive. So this is useful for cleaning up maps, but also, you know, they make it a little bit difficult because they don't want you to accidentally delete maps that are important. This is also a reason why we keep our base maps in permanent and we work in a different map set. You cannot delete a map that is in a different map set from the map set that you are currently in. So if I keep my maps in permanent and I'm working in this case project 2, I cannot physically, Grass will not let me delete something that is in permanent. So I'll just show you that, and it's going to be real dangerous looking. I'll go back to my G remove and I will pick a map, select raster, pick a map that's in permanent, my SRTM. I'll even check the force and I'll hit run and it'll just give me an error. This cannot be removed because it's not in the current map set, right? Grass is being nice to you as long as you follow along with the workflow that it expects you to be doing. Okay, so that's just some basic map cleanup stuff that you may need to know if you're getting all cluttered, right? Let's get to the meat of the issue that we're talking about today, which is actually interpolation, okay? So what is interpolation and why is it important to know? Well, at its very basic level, interpolation essentially fills the gaps in spotty data. So if we think back to our model of the world, we have a specific resolution or specific points that we captured information from. But we have a lot of the world that's sort of missing between all of those points, or that we're not capturing at a specific resolution. Interpolation is a way to take the data points that we have and to estimate what things might have looked like between the data points that we were actually able to gather. And so what it's doing is not gathering new data, but it's taking the data that we have and using it to estimate the parts of the world that we couldn't go observe or that we didn't go observe and get data from. So in a sense, it's a model, a way to model gaps in the data, and it's a very inductive modeling method, meaning you have to have a set of data, and then from that data it derives some predictions. So it is kind of like a predictive model in that sense. So I have a graphic here that may make this a little bit clearer, hopefully. There are a variety of statistical methods to actually achieve the interpolation. So what we're looking at here, this is like a line, right? This is what we call one-dimensional. We're just sort of moving from the left to the right, on these different methods. So if we have one point that we gathered in this brown line here, and we have a second point that we gathered in the green here, but later on we realized that we want to actually know about a location that's somewhere between those two, this black point right here. How can we estimate what the value of the black point will be if all we know is the value of the green and the brown points? Well, there are a variety of ways to do this. The simplest one is what we call 1D nearest neighbor, or just nearest neighbor. And that says essentially we treat the world as discrete units. In a neighborhood around this green dot, everything's going to be exactly the same. And in a neighborhood around this brown dot, everything's going to be exactly the same. If our black dot is closer to the brown dot than it is to the green dot, then the black dot is going to be exactly the same as the brown dot, right? Very simple method to estimate what the black dot would be. Not all natural phenomenon of the world sort of adhere to this. There are some things that do, but mostly we have a continuum, a sort of gradation between the two, that this very stepped estimation is sort of missing. So what can we do to solve that? Well, the easiest next step is to do a linear interpretation. That's to say that we treat the difference between the brown dot and its neighbor, the green dot, as a very straight line, so going directly from the brown dot directly to the green dot in a very straight line, the shortest line between those 2 points. And you'll see here when we do this, we can just calculate the slope of the line, which is, you know, the rise over the run. and we can actually find the distance between these two things. And if we know the distance for this run right here between the brown and the black, we can go over and up, and then we can get an estimate very, very easily, knowing the slope of this line for what this value ought to be, right? And we see that it's actually a different value from the nearest neighbor, which had the step function. In this case, we have a transition along a straight line between the 2 points, and we say, okay, the black dot is closer to the brown dot, so it should be more similar to the brown dot, but it's on the way to the green dot, so it needs to be a little bit, in this case, larger or higher, taller than the original brown dot, right, according to this function. Well, that turns out that does a better job, for sure, of this, but that would mean that there would be sharp angles, right, at every transition point that we actually measured. And we can get a reasonable estimation of the world like this, but we know that the Earth surface is kind of curvy, right? So that takes us to this other set of methods, cubic or spline methods, in which case we have to make a much more complex function. Instead of mx plus b, which is the line function here, we have to have a polynomial function of some kind with a bunch of exponents to make this curved surface between the two. So in this case, we have the brown line, or the brown dot and the green dot. We have this curved function between the two, and we need to shoot out a little bit. We need to add a couple of extra data points, a red dot and a blue dot that we've observed, and we can fit this curved line between them, and basically we're getting a better estimation of the transition between the 2 points, because it's not a step function and it's not a straight line. It's actually curved, much more similar to what we would expect the Earth's surface to be. And now when we do the same thing again, the black dot is closer to the brown dot, on its way to the green dot, but because the line is curved, we get a height that's a little bit actually less in this case than the linear estimation over here, probably closer to what it really was if we were to go observe this point in the real world. So we can see we're basically getting more and more realistic, but we're requiring more complex algorithms, and thus our computers to work a lot harder. What we have down here is essentially expanding this. This is just for a line, but this is for actually a surface, a two-dimensional surface, just like as we walk over the surface of the Earth. And here we have the same thing, but in 2 dimensions, so along the x-axis and along the y-axis, and then the z-axis is height over here. And we have these step functions, and we're still doing the same thing, estimating the black dot, but now we have to figure out which of the 4 points it's closest to. And we have the same thing over here using a linear or bilinear in this case, because we're going in with 2 lines in this direction and then back into the graph sort of in 3D. And here we have bicubic, so wow, we need a much bigger neighborhood. And we have all of these curvy lines and all of these dimensions. But again, the point here that we're estimating with our interpolation is going to be probably closer to what it really would be if we were to go to that point than either of these other 2 methods. Okay, so this is a little graphic to help us wrap our minds around it. What does this actually mean in a real scenario for applying? So what would we actually use interpolation for? And there are actually a variety of things we would use it for in a GIS. I'm going to talk about 2 things, right? So the first one will be creating a surface from data in our vector table. The other one will actually be estimating increased resolution of a raster map. So what we're going to do is we're going to start with the Wadi Halsa survey data, and we're going to look at the table that we have. And we need numerical data to do this. So we basically have 2 columns here. We have max length and max width. I'm going to work with max width over here because I can see 300 is the maximum and 1. Yeah, okay, I'll just work with this. And what we'll do is we'll turn the column of data here, we'll use those as our observed points, and we'll use an interpolation algorithm to statistically fill the gaps to get a continuous surface in the area of the Wadi Halsa survey that give us a good just visual summary of what this attribute actually looks like on as you traverse the entire area. So what we want to do is constrain our computer to just working in the area of the survey here, because we have no data over here and we don't want it to provide us an estimate of the maximum width of a site over here because we're way far away from our nearest data points. And it will give us an estimate over here, but it's going to be completely and totally inaccurate because it's not based on any real data. So in this case, what I'm going to do is use a vector tool to draw a boundary around it. So we'll call a convex hull, essentially giving us a delineation of the area in which we actually have some points. So under that, to do that, we go to vector and we go to generate areas from points, and we just pick this v.hull, convex hull. Body has the points here. And we'll just say WHS boundary area, right? Under the optional tab over here, we can choose a couple of different things. Typically the defaults are fine. We hit run like this, and you see what we've done. We've basically got a boundary area. If I drag it down in my layer tree, drag it down in my layer tree, you see it just drew a line around where we had all of our points. So it's not perfect. It doesn't go up into these areas over here. It's just the area that basically contains most of our points. In order to use this to constrain what we're going to do in the next couple of steps, which is to make the interpolation, we need to actually translate this from vector polygon, which is what it is right now, to actually a raster map of ones and zeros, a binary raster map. And the easiest way to do this is to go under File, Map Type Conversions, and then go to this vector to raster, v2rast, v.2.rast. And it's real simple. You take boundary area, which we've got selected already here, and we say WHS boundary, and I usually put rast because I've translated this. Source of the raster values, we're just going to pick, you can actually make this be from a value in the table, but we're just going to give it a constant value, so we'll put this thing that says val. Over here under the attributes, actually it's under the optional tab here where it says raster val, it says 1. So that's basically going to take anything that's inside the polygon over here and make it value 1, and everything outside will be null. Okay? And the selection, we should just make sure we're picking only the area. That's all we want. And we hit run, and there we go. We have a raster map, this pink thing over here, which essentially is all value of 1. So if I query it, you get all values of 1 inside, and then outside is no data or null values here. Fantastic. So we are basically ready at this moment to move forward with our interpolation routine. And what we're going to do is go to the raster menu here and down to where it says interpolate surfaces. And you actually see that we have a variety of options here. We have bicubic methods that we saw are the best. We have the IDW, which is basically the nearest neighbor type analyses, and we have a couple other sort of more special purpose things over here, spline tension and raster contours and that kind of stuff. Normally what I would suggest is that we use this cubic interpolation over here because it's going to make the best looking map, but it takes my little computer here a very long time to process. So we're going to do the fast and easy one, which is inverse distance weighted from vector points, v.surf.idw. And what we're going to do is pick our vector map, which is WHS sites. We're going to make this output map. We're just going to call it site size, because that's really what we're interpolating here. For our values, we're going to pick the column max width, which we set earlier. And we're not going to change anything in settings. These are all generally fine. And, oh, I forgot one really important step that we need to do. We actually need to turn this pink raster map into a mask so that grass is only going to work within it. And that's really, really simple. We go to raster menu, and we go to mask, r.mask. And what we do is we pick our map, that's the WHS boundary rast, and what it's going to do is going to make a special map that essentially is going to be called mask in all caps. And as long as that map exists in our map set, grass is only going to work within the boundaries where there are values of 1 in that map and not in any value that was null. So we just hit run on that. And all of a sudden you see the rest of the map disappeared. And actually if we were to look underneath this, we would actually see that the Wadi Hassa SRTM is there. So the map, this didn't delete this part, it's just literally masking that like masking tape when you're painting a room. Okay, so now we're only going to work in this little segment of the world. This is a really handy little tool. We go back to our v.surf.idw, we've got everything set up, and we can hit run, and there we go, it's going to chug along. It's going to chug along. We could have increased the speed by actually zooming in on this area. In fact, I'm going to do that. I'm just going to stop it in the middle, and I'm going to zoom in to my Wadi Hassa sites, zoom to selected map like that, and then I'm going to set computational region extent. So we've done 2 things. We've masked out stuff, and we've zoomed in, so it's totally going to ignore this rest of the area. And now when I hit run, it's going to go a lot faster, you see. So what it was doing before is actually, even though we masked out and it was all null, it was still trying to go from way over here over and just to see if it needed to make any calculations in those areas. Alright, so we are almost done here. We're almost done. We're almost done. And there we go. Alright, so we're going to close that for now. And it doesn't look like much now because what we need to do, site size here, is to set the colors a little bit. Sorry. Go down to set color table, and we'll just pick a different color ramp so that we can see things better. I'll pick this BCYR. We'll hit run. Alright, so now we can see what's going on here. Let's add ourselves a little raster legend. Yeah, that's okay. So here we are. So essentially, the sites that are very wide have influenced our interpolation here to essentially show in red or yellow, and the sites that are really small are in sort of showing in blue. So basically what we're seeing is a continuous surface that's showing us about the sort of patterning, go down, there we go, in site size as we go across the region. So we basically see that a lot of the large sites are clustered over here. This is sort of showing us, you know, that over here we have a lot of large sites, and yet in the rest of the Wadi over here we have a lot of clustering of small sites. And what's really cool is if we remove our mask, so if we go back to our mask over here, and we go down to remove, and we just hit this, we hit run, it deletes it, and we sort of get our area back over here. We sort of zoom back into the SRTM. Oh, it looks like it actually ignored our mask, which was kind of annoying, but we set the region, so that was good. So it did that for us anyway. We can actually see how this maps onto the landscape as we moved out like this. Okay, so that's really cool. We can see how we can make a bunch of layers of maps right here with various information from inside our points file. We can see how if we were out with a GPS and we took a bunch of points and actually recorded elevation, we could actually make a digital elevation map or an estimation of a digital elevation map by using the elevation value to interpolate between the areas over here. This is sort of in addition to like a thematic map for like the site. So if we wanted to do a thematic vector map, we would go over down here, we would say set color table, and we would pick attribute here, and we go to a color table, or we pick the column, we'd pick site width, and we'd pick the same color table, BCYR, we'd hit run, and it would change the colors of the points. So let me just refresh the map over here like that. And they look like they disappear, but that's because they're the same color. So what we would do is get rid of that. So we can actually see, oh yeah, there's a real red one, there's a little yellow one, you know, there's a bunch of blue ones. But when we translate this into a surface like this, the pattern may actually be a little bit easier for us to see, because it sort of says, oh, well, if there are a lot of big sites over here, there ought to be more big sites, so we'll just sort of make the coloring show that. And we really can see that they're clustering with a bunch of big sites over here. All right, so that's the method for turning discrete data taken from vector points into a surface. What if we have a surface, we have this 30-meter SRTM, and we want to actually use an interpolation method to make the resolution finer, right? So importantly, we gathered this data at 30 meters. We're not really going to gather new data at, let's say, 10 meters, but what we can do is estimate what the curvatures between the two adjacent cells would be at a finer resolution of 10 meters. And what I'll do, let me just remove that, is zoom in to a little area, again, because it takes a while for my computer, and interpolation methods are very, very computationally expensive. And I'm going to set the computational region to match my display right here. So now we're only going to work in this little square. Even if I zoom back out, we're only going to work in that little square. And what we want to do is go to the raster menu, develop raster map, and then these resampling methods over here. And in this particular case, because we zoomed in so much, we can use the B-spline, the spline methods that are much more accurate. And essentially what we do, we're going to pick our input raster map, our 30-meter SRTM, and we'll say, I'm just going to call this central Hassa, because I only zoomed into that little area, 10-meter DEM, right? So that's really what we're going to do. We're going to take the 30-meter and we're going to estimate what the landscape would be like at 30 meters. And there's a bunch of stuff that you can tune. Some of this stuff can be important for a variety of reasons, but for now we'll just leave it all as its default, because, well, you know, the default values are pretty good. So we can't just hit run now, because our resolution in our region settings is still 30 meters, and what this would do is take the resolution of our input map and make it match whatever resolution we've set for our region settings. So what we have to do is update our region settings with g.region, sorry, not the p, set region, g.region here. We go down to the resolution tab. So actually, it's actually good that I hit print. So we see that our north and south and east and west resolutions are 30 meters right now. What we want to do is to set them here, resolution tab, and the value that says res, 2D grid resolution. We'll change it to 10 meters. And we'll hit run like that. And now if we go to region, display region over here, we see it says the region is 10 meters now. So now, even though our data is at 30 meters, anything we do is going to be done at 10 by 10 meters. So what we want to do is actually do an estimation using an interpolation method, a cubic spline interpolation method. So we've got it set up right here. We just hit run, and it actually is going to take a little while. It's got to chug through this. What it's doing when it's saying subregion, all of this stuff is actually working on a part of the map, part of the map, part of the map, part of the map, and then it's going to patch it all together. And it does this just to make it easier on your computer. If we did this for the entire Wadi Hassa region on my little computer here, we'd probably be here for a good half an hour to an hour. But as we can see, because we zoomed in, it did it relatively quickly. And really what you can see, remember we set our region extent, so it's only doing in this area, and this is 10 meters. If we zoomed in, we could actually see. It's a little hard to see the pixels in this particular color scheme, but you basically can see what I mean. We've got finer details that the routine estimated between the original 30 meters and the new 10 meter DEM. And probably the best way to drive this home is to go into the 3D view over here and sort of have a look at the two services. So basically I set this up a little earlier. In the data tab over here, I have both the 10 meter DEM and the 30 meter DEM set up over here, and I've sort of dragged the 30 meter DEM sort of higher, right? So if I select it over here, I can move the Z, I can actually move the maps up and down in relation to each other. And I've also made sure that I set the fine resolution on both of them to be 1. Actually, just make sure I did that for this one. Set it to 1, like that. And I also went to the Analysis tab and I set up a cutting plane. Picked plane 1, and I can rotate the cutting plane around it so we can actually be looking directly into them. And I think what I'll do is I'll just clear the difference between the two of them. And now I got my sort of view tab here. And if we kind of look at these things, let's just do it like that. And we zoom in. You see, this is the 30 meters. Actually, show you. See, it looks like staircases. Because right now we're actually operating at a 10-meter resolution. And so the NVIS, or the 3D view here, is actually show us the 3D steps. So these are the actual raster pixels at the 30-meter resolution that we originally collected our data in. So even if I zoom in just a little bit more like that, you can really see the steps, right? But if I show us the 10-meter DEM, which is down here, we can see it's smooth because we've interpolated between all these steps. We basically removed the stepped nature at this 10-meter resolution. If we go out there at any given pixel, it's an estimate, right? Because our data was collected at 30 meters. We're estimating a smoothing of that data at 10-meter resolution. But it's probably pretty close to what the surface really looks like in the real world. So again, we're not gathering new data, we're just estimating from our original sparser data set at a finer resolution. So it's a really efficient way for us to basically use our instruments if we can only do 30-meter resolution, or if we're out in the field and we can only gather GPS points every so often, to basically fill the gaps between them, to estimate what it would be like between them. And for us, this is really great because maybe we can only get data that's at 30-meter resolution, but we are modeling something that has to be modeled at a finer resolution, like the flow of surface water across the topography. We want to model that at a finer resolution. We can interpolate down from our coarser data to a finer resolution. Even though it's not real, it's a model, it at least puts us on the right physical scale to be able to do the kind of analysis that we need to be doing without relying on finding a really fine resolution data set that was gathered with LiDAR or something like that. Okay, so that's basically what we have for interpolation methods. This is not part of the third project, but it's a really useful set of skills for you to have, and I encourage you to fool around with some of the interpolation methods, both interpolating from vector points, but also interpolating, resampling the maps. You have to be really careful about setting the regions and all this kind of stuff. So once you've set this region, you want to maybe reset it back to the 30-meter by going to set computational region from selected maps, and that will zoom us back out to the whole entire Wadi Hassa region instead of just this one little area that we were working in. I encourage you to play around with this stuff and to practice some of these tools, exploring some of the map managing little cleanups and all of this kind of stuff, and the conversions and all of this other thing, and with the mask and a few other stuff, as well as the interpolation methods. And when we come back, after the next week actually, we're going to do view shed analysis. So that's going to be the sort of next thing on the docket. Yeah, so that's what I got for now, and we'll talk next time.